Welcome everyone, this is Giridhar. This is session 1.5 of the Quantum Computing Podcast at CFRC. This will be a brief linear algebra primer in which we provide enough context so you can understand both Aniket's next series of lectures and his later lectures on quantum information theory and sort of our coverage of that. This will largely be focused on linear algebra that is particularly relevant to quantum computing, so it'll not be an overall general coverage of the field, but definitely you can pick up some stuff from this that could inspire your own exploration, definitely. Without further ado, I think we can get started. Okay, so now we will begin with our first section. So here we will define the two basic fundamental operations between vectors and scalars. So here we have two vectors picturized as lists of numbers. In particular, here they have three numbers each represented by an arbitrary variable, but the number of elements doesn't really matter. You will get the idea of what the addition operation does here. So that's the first operation we're going to define. For vector addition, you simply add component-wise, which means that A is added to the corresponding, being the first element of vector 1, is added to the first element of vector 2, and so on. So I apologize for my handwriting. So this is the vector addition property. And then as opposed to this, where we have the scalar multiplication property. Scalar is probably a term you've heard before, especially if you've taken a physics class. But basically, it is a regular number. In our case, it's going to be a complex number because in quantum computing, we're going to deal with a complex vector space. Okay. And scalar multiplication is basically the multiplication of a vector by a scalar, here a complex number. So if we perform this scalar multiplication, we basically element-wise again multiply this vector. So we'd get a new vector with entries ka, kb, and kc. And so this is how we define vector addition and scalar multiplication. Okay, so now we will begin to define a vector space. So first of all, a vector space is basically a particular set of vectors. So this is a vector space. But a vector space also has some more specific properties. And the most important of these is called closure. Please bear with the horrible handwriting. But closure basically involves the two fundamental operations we mentioned in the previous one. So if we have two vectors x and y in a particular vector space, that is their vector elements of that vector space, then by closure under addition, we can say that x plus y, the vector x plus y, must now also be in the vector space V. And this is called closure under addition. On the other hand, if we have x again in V, and we have C in what I'm going to call C, big C, this is actually the one-dimensional complex. It's not a vector space really. It's the field of complex numbers. So basically, C over here just represents some complex number. Perhaps that character is a little bit confusing, so I could say K is in C. And this is only specific because we use complex vector spaces in quantum computing and quantum mechanics. So then we can say that Kx must be an element of V. Basically, if you multiply by some scalar from the complex set of complex numbers, or if you add two vectors from within a vector space, you should not get a vector that is outside the vector space. This is the idea of closure under addition and under scalar multiplication. The other property of a vector space is that it has a zero element. Um, and this zero element has the specific property that viewed as a list, it basically has just all elements are zeros. This also bears the property that if you have x in V, I'm presuming x is in V, and we add the zero vector to it, trying to get it to autocorrect, there you go, you should get back x. Right, and this makes sense. As we define the vector addition process, if you add zero to every component, it's not going to change, so you're going to get back x. Here is just a quick note. From sort of the next part of this, we will start to refer to every vector using what is called the bracket or Dirac notation. Um, and so every vector will be represented this way. This is a column vector representation. We would represent it uh, the other way around, that is like this, if it was a row, but we'll come back to that. Um, so generally we would represent all vectors this way. However, the zero vector is an exception, and Nielsen Shuang actually mentions this, and I thought it was a very good point to make. So I'm repeating that. This actually refers to the zero state of a qubit. Within quantum computing, we have a qubit that could be either in state 0 or in state 1 when you measure it, according to a particular basis of measurement, but we'll come back to all of that. For now, all that's important is that you don't want to use the Dirac notation when you're writing the zero and when you're writing the zero vector as meant over here. You'd be better off just writing it as a bolded zero. I can't really bold it in Microsoft Whiteboard, but I think you got the idea. The last quick note I wanted to make was about the vector subspace. A vector subspace is basically a subset. Um, a subset of a vector. Uh, of a vector space, my bad. Um, and this contains, some vectors, which is why it's called a vector subspace. The important thing is that this also satisfies closure, namely that it satisfies, all elements in this vector subspace. When multiplied by a scalar in the field, produce another vector within the subspace. And when two vectors in the subspace are added, they produce another vector in the subspace. The zero vector is also likely present within the subspace, but the closure is the important property for subspaces. Okay, so now we will introduce Dirac notation. This will just be a brief introduction. There's actually nothing too significant in the way we will use it. But first of all, we have to, this is also called bracket notation. So basically the ket, which looks like this, and that is a very poor rendering of the Greek letter psi, which is often used to represent quantum states. So this is a ket. Basically, a ket is a column vector. Depending on sort of the vector space and its rules, there will be different ways to get between a ket and a bracket and a bra, but the that will be defined as I managed to find a blind spot on my screen, but it will be around here. Yeah, that should be fine. So this is the first part of the bracket, which is bra. It is effectively a row matrix or row vector, not a matrix. I'm sorry. It's a row vector, and this is known as the dual to the ket. I don't think we need to worry too much about that. We won't use it, but This is just so that you understand what we're doing when we apply, say, inner products and all of that in the future. And perhaps for those who are not actually intending to use this for quantum computing or want to use this for something like machine learning, you would have to convert sort of the notation and thinking into standard ways of writing. So, for example, this would really be thought of as like a transpose in real vectors, in a real vector space. And by a real vector space, I mean a vector space whose coefficients and constants all come from the set of real numbers. So now we will just quickly cover some basic matrix operations. So if we have the complex number z, and we take its complex conjugate, we will take a quick example of z, but basically this takes the real component of z and subtracts the imaginary component of z as it is currently present. So for example, it would be if you took 1 plus I as z, where I is square root negative 1. Then the complex conjugate of 1 plus I is equal to 1. And otherwise the coefficients don't change at all. But the sign on the complex term basically changes. So here we get 1 minus I instead of 1 plus I. So there is an important operation that's also related to this, but applied to matrices. And it's called the conjugate transpose. Before we cover a conjugate transpose, actually, let me just quickly cover what a transpose does. So for a particular matrix A, a transpose is written this way. This would be A transpose. And what that effectively does is it flips all elements in A over the diagonal. So if this is the diagonal within A, and let's assume there's some elements in this matrix, then it flips all of them so that the element at some index n comma n will then be at index n comma m. So for example, if we have the matrix we can then say that A transpose is equal to at 1, 1, we have the number 1, and this is going to stay the same. At 1, 2, that is row 1, column 2, we have 0. So at 2, 1 in this transpose matrix, we're now going to have 0, which means it will be over here. And then at 2, 1, second row, first column, we have negative 1. So at 1, 2, we'll have negative 1, which will be here. And similarly, the 1 will get flipped over to this side. So this is how the transpose operation works. In the course of this linear algebra part, we will very often use the operation called the Hermitian, which is written as a dagger. This is called the dagger. And basically what this does is it takes A transpose and then complex conjugates every element in A. So naturally, if A was a matrix of real entries, then A dagger would be equal to A transpose. But if it's not, then it's going to basically flip the signs on all the complex parts after performing the transpose. Okay, that's all I wanted to cover. So now we will start to get into the heart of linear algebra. In particular, we'll now discuss what a linear combination is. So let's say we have some vectors v v1, v2, and v3, we can also scale each of these vectors as we saw by scalar multiplication. So we could do kv1, for example, if we wanted. And actually, we could combine both the fundamental vector operations that we defined, and we could add up the scalar multiples of each of these vectors. So we could write with some arbitrary scalar ki, right? Um, and so this process actually produces what is called a linear combination. Um, so a linear combination is a combination of this of scaled multiples of multiple vectors. Um, and so the other thing that is often used with a linear combination, um, and this is one of the most fundamental, you know, animals of linear algebra, but what is often used with linear combinations are the summation notation. So I will just introduce it here. Because we will be using it quite frequently from here on. Mm. If you're from a computer science background, it definitely can help to think of the summation notation as sort of a for loop, because as we will see later, you the the iterator, that is I, can be thought to both move over individual numbers and also over values like eigenvalues. Um, don't worry if you don't recognize that, we will cover it. But basically, the idea of summation notation is if we give this I a starting point and we give it some ending point. Often this is a variable, but just for the sake of simplicity, I can give it a value 5. Um, and then if we do k sub I and v sub I, what we end up producing is k sub 1 plus v sub k sub 1 v sub 1. Both of these are i's. K sub 1 v sub 1 plus k sub 2 v sub 2. And we keep adding in this way until we get to k sub 5 v sub 5. So this is what the summation notation is. The thing with linear algebra is that a lot of what we're going to be covering is very general, and we're not really dealing with the sort of the direct numerical problem solving side of linear algebra. This will be focused on abstract linear algebra. So very often you will not actually get numbers like this. You will not get a starting number and a final number. Instead, I is just assumed to iterate over all possible iterable values. It depends on what I represents in the context and what values it can go over. Okay. Um, so now we can begin to explore what the implications of linear combinations are. In particular, we're going to deal with this concept called span. And this is, again, a very foundational concept of linear algebra. But span is the set of vectors for a set of vectors, say v1, v2 to maybe vk. A span of a set of vectors is basically the set of all their possible linear combinations. So it's the set of all possible outputs to the function um, of c1 through ck, which is equal to c1, v1, c2, v2, effectively their linear combination. if the span of a set of vectors is a particular vector space, that is, if span of v1 and v2, for example, is equal to R2, the space of two-dimensional vectors which take their elements from the set of real numbers, then we say that this set of vectors spans R2. Now, we also call it a spanning set of R2. Now, let me just give you a quick example and one that is relevant in the quantum context before we move on. In particular, we can talk about the two standard basis vectors. That's actually kind of a technical term, and we will define it soon. But for now, you don't have to worry about what it is, other than that actually this is a spanning set for C2. C2, which is the set of all two-dimensional vectors that take their elements from the set of complex numbers. And C2 is, and not C2 in particular, but Cn is the set of vector spaces that we care about most in quantum mechanics. So in particular, there is a spanning set for C2, which is 0, 1, and 1, 0. For those of you who are curious, this is actually addressed as 1, and this as 0. And these are actually the I think it's a little bit complicated to understand for now, but definitely these, you can sort of get the idea that these represent the two measurable states of a of a qubit, which is a bit, but in quantum computing. And I can actually prove over here that these two vectors span the entire complex vector space. So if we take the entire vector space C2, that is, so if we take this arbitrary C2 vector A, B, and we take C1 times 1, 0 plus C2 times 0, 1. Basically, what we have to show is that for every A and B, there is a corresponding C1 and C2 that will produce A and B. So what we can do now is actually we can say that C1 is equal to A and C2 is equal to B. In this case, what we can then say is that, and if we try this out, that is, you will get A1, not A1, A0 plus 0B, which is going to yield AB. So as you can see, this is a spanning set of C2, in that any vector in C2 can be expressed as a linear combination of. Okay. So there's another concept that comes out of the idea of linear combination, and in some ways it's the antithesis to a span. And these two concepts are particularly foundational to linear algebra, so make sure you're sort of the same. So the other idea that we will now cover is called linear dependence. So if we have a sequence of vectors, v1 through vn, if any vector in here, say some vector j, some vector vj, if it can be written as a linear combination of the elements of the vectors within this sequence, excluding itself, then we say that this sequence is linearly dependent. Let's take a quick example so that you sort of get it and I don't befuddle you with my uh, long-winded explanations. So we could take the three vectors. V1 is equal to 0, 1. This is sort of a simple set. I'm just taking it for representation. 0, 1, 1, 0. And we can then take V3 to be 1, 1, let's say. So now if we have the set V1, V2, and or the sequence V1, V2, and V3, the question then is this set linearly dependent? And the answer will be yes. And it does have something to do with the fact that V1 and V2 are actually a spanning set of the complex vector space to which V3 also belongs. But the really important idea here is just that V3 is equal to V1 plus V2. In other words, there is some linear combination of the other vectors in the sequence that can produce V3. So as a linear, it's not really contributing anything in one sense. So we call such a sequence linearly dependent. More formally, the way we generally write in order to understand linear dependence and independence is we write the entire linear combination as a sum on one side. So it's Ci times Vi, where C is a scalar constant. I will move my hand once I've done. Multiplied by a vector V sub I. But the idea is that this goes from, say, 1 to n, and we set this entire thing equal to 0. Basically, what this ends up telling us is, is there some linear combination? In the case of V1, V2, and V3, as we described above, is there some linear combination such that these can cancel out? And in the case of V1, V2, and V3, it would be C1, that is the multiplicand for V1, would be 1. C2, the multiplicand for V2, would be 1 as well. And perhaps the multiplicand for V3 would be negative 1. And so we would end up getting 0. The idea is, if there is such a relation, then we can say that this sequence of vectors is linearly dependent. In particular, the general formal way we understand this is something called a dependence relation. We say that this sequence of coefficients or constants, C1 through Cn, is a dependence relation on this sequence of vectors V1 through Vn. And let me just write that down, dependence. I don't know if you can understand anything at all, but dependence relation. And so there are two kinds of dependence relations, and we can sort of discuss that now. So there are two kinds of dependence relations. One of them is where every single coefficient up to Cn is actually equal to 0. And this satisfies our dependence relation equation over here. Because if you multiply all vectors by 0, you're going to get 0. The thing is that this is not actually very significant. This is true of any vector. It doesn't tell us anything about the vector at all. So we call this a trivial dependence relation. On the other hand, if at least one of these coefficients is non-zero, then we say it's non-trivial. So if a sequence of vectors has only the trivial dependence relation, we say that it is linearly independent. Um, and I just like to use the short form Li because sort of writing is expensive in this environment. But uh, such a sequence is linearly independent. But if there's a non-trivial dependence relation, that is, there's a dependence relation in which some coefficient is not zero, then we would say that the sequence is linearly dependent, which here I denote as. Okay, so now that we've discovered spanning sets and linear independence, we can come to what's called a basis. A basis basically is a spanning set for a particular vector space, which is also linearly independent. I think it would actually be a little bit faster if I just typed some of this, which I will do. It'll be a little bit easier to read. So, the spanning set is also linearly independent. Okay, cool. So a basis is a spanning set that is also linearly independent. And for any given vector space, there will always be a basis. So if a sequence of vectors, and this is sort of maybe appears slightly unrelated to begin with, but if there are a sequence of vectors, say of length k, that is, there are k vectors, and each of them belong to Cn, the vector space of complex numbers of dimension c, dimension n. In this case, yeah, I'll just put n there. If n is less than k, that is, the number of elements in every vector is less than the total number of vectors, it must be linearly dependent. On the other hand, if k is strictly greater than n, that is, the number of elements in the set, or not, rather, the number of vectors in the sequence is greater than the number of elements in each vector. Um, okay, so if k is greater than n, it's not a spanning set. This is actually a little bit more based in the numerical side of linear algebra. I wouldn't worry too much about this. The important idea, however, is that uh, effectively, if you have the number of elements the number of vectors in your sequence is, if the number of vectors in your sequence is actually equal to the number of elements in each vector, that is their dimension, uh, then uh, then it can do both. That is the only case where a set of vectors can be both a spanning set and be linearly independent. And which, since that is a definition of a basis, a basis is effectively the case where n is equal to k. Okay. And I use this word dimension. The number of elements in a basis is called its dimension. So we discussed actually what was one basis of Cn, and we call this the standard basis of C2, rather. And we call this the standard basis. And so this was 1, 0, and 0, 1. And as you can see over here, the number of elements, that is the dimension, is 2, and the number of vectors in the sequence is also 2. So this is a basis. That is not enough for it to be a basis, but that is a necessary but not sufficient condition. Okay. In particular, we can just quickly talk about the standard basis vectors. This is a little bit more directly pertaining to real vector spaces, but it's actually pretty much the same with a complex vector space. For a standard basis vector, and these are denoted with the letter E, and there's some subscript and some superscript. So the superscript is going to be n, and I can call the subscript something like I. And n basically indicates the dimension of your vector space. And I is sort of, it's kind of, you could say it was kind of like an iterator. It goes from 1 to n. And there are n vectors in the standard basis, right, which makes sense because the number of vectors in the sequence will be equal to the dimension of the sequence. And in particular, EI is defined as this vector, which has zeros everywhere else. So every other element is 0. But just at the ith element, we have a 1. And again, everything else is 0. And in fact, the vectors I showed you before are actually standard basis vectors for C2. And as you can see, this is E0, or sorry, E1. This is E1, E1, and this will be E2. They have zeros everywhere else and ones exactly at the positions mentioned. Okay, so now we can start working on linear operators and matrices. Operators and matrices. Okay. So a linear operator is a map. That's perhaps slightly unfamiliar terms, but a close analog of this is a function. So it's a map or a function from some position in n to n. The way we write this is for a particular linear operator A, we say A takes Rn to Rm. Okay. In particular, we call them linear operators because they obey linearity. I'm not going to prove it, and that's going to be a general trend, I think, for the most part, because we have quite a lot to cover. But you're definitely welcome to try it, and it's not too difficult to prove. So if you have A, the operator A, and I'm actually going to write this because it's a little bit difficult to type, but if you have the operator A and it's applied to summation over I of some constant A sub I times V sub I. So this is basically a linear combination. This is actually equal to summation over I of A sub I, which is the coefficient, times the matrix A, or the operator A. Okay, maybe I gave away something, but the operator A applied to the vector V sub I. So this is called linearity. Yeah. We will sort of just quickly go over some general linear operators that are important, and we'll cover their relation with the matrices in the next part. So another important linear operator is called the identity operator. And this is generally written as I. However, the identity operator will sort of vary in shape and representation according to the different vector space. So, which is why I'm designating that this is I as corresponding to the vector space V. And basically, what this I does is that I V applied to the vector X gives you the vector X. So it's not very interesting, but it's definitely something useful, and we'll come to that soon. Another important operator is actually one you wouldn't think is an operator, and that's the zero vector. It's not actually the zero vector, but we call it the zero operator. So zero applied to, or zero applied to, it's a linear operator here. Zero applied to x will actually always return zero, and I'm afraid the notational thing is becoming a little bit difficult to show at this point. But this is an operator and this is a vector. So that's good to know. Okay, so now we can explore the relationship between linear operators and matrices. And first of all, let us consider this assertion. The linear operator's action on all the basis vectors determines its action on all vectors in that vector space. Okay. Now this may not make any immediate sense, but let's think about it more carefully. Before that though, what we have to do is we have to redefine the way we see a normal vector. We have the sufficient tools to do it, so let's do it now. If we have a particular vector, and I'm writing this as a horizontal list simply because that's the easiest way to type it. This is intended to be a vertical list for now. It doesn't make too much difference really, but so if we have a vector that simply lists the numbers from 1 to 5, what is this actually? We could say that this is a list, but if you look at it in the context of linear combinations and basis vectors, really what we are doing, and usually this is in the standard basis, what we are doing is we are saying V, and if we were to say, the ith element of B is represented by Vi, then we would say what we are doing is we are taking V1 and multiplying it with E1. E1. 1 is a subscript. It indicates the first standard basis vector. And then adding that to V2 E sub 2 plus V3, E sub 3, and so on till V5, E sub 5. So what we are really saying is that any vector is actually a linear combination of the basis vectors. Okay, that's significant. Before this, we mentioned the property of linearity of all linear operators. That is, if A is applied to a linear combination, we can take the linear, if the operator A is applied to the linear combination, then we can take the linear combination, the same linear combination of A applied to each of those basis vectors. And that's exactly what we are going to do now. In particular, what we want to, and this is exactly where this theorem comes from, but what we want to do now is to find a matrix form of a linear operator. Now, most of you should be familiar with matrix multiplication, but what we do with the relationship between linear operators and matrices is that linear operators can be written as matrices when you specify a basis. When this is done, what we do is we see what impact the linear operator has on each of the basis vectors of the vector space. And then we actually just list each of those affected basis vectors as the columns of the matrix. So let's just take one example. I'm introducing this matrix, which would be, this is not a great way to create a matrix. So I'm introducing this matrix X, and as you'll see later, this is actually an important matrix in quantum computing. But basically, this matrix X, rather than telling you about the matrix, I'll tell you about the linear operator first. What this linear operator does is it takes the first basis state that we discussed before, it takes 1, 0, and turns it to 0, 1. And then it takes 0, 1, and turns it to 1, 0. Okay? So now what we want to do is to find a matrix representation for X with respect to the standard basis for C2, that is 1, 0, and 0, 1. So actually over here we can see that we already have the impact of the vector on the basis states. Of the operator on the basis states. X as applied to the basis 1, 0 produces 0, 1, and as X is applied to the basis 0, 1 gives us 1, 0. So now we can create a matrix that actually just contains these affected basis vectors. So it's going to give us 0, 1. We're just taking this and listing it, and 1, 1, and 0. Okay. And this is actually the representation for the X matrix according to of the X operator according to this basis. The important thing to note is that there is a matrix representation to every linear operator, but it is completely dependent on what basis you're viewing them in. As we will eventually cover, perhaps later in the quantum computing series, but there are multiple bases that both span the complex vector space C2 and are linearly independent. That is, they can satisfy all criteria of bases. And all of them will not look the same. You know, another one is 1 over root 2 times 1, 1, and so on. So these are referred to as the plus minus states. But the important point is that these are, I don't want to confuse you with some more vectors, but the important point is that these are also basis vectors, And the way you would flip these vectors between each other, you would not use the same matrix would not do that. Okay, so here's just a quick note on linear operators and their composition. If you have an operator A and it's applied to the vector V, this produces another vector, which we could probably then call W. But we could also apply another linear operator B to W, as long as W is in the domain of B. So the way we could write this without actually going to an intermediary state would be B of a V, and we actually can see that this is nothing but BA applied to V. And this becomes significant when you have a matrix representation. What you actually have to do in order to apply multiple linear transformations or linear operators to a particular vector is that you would multiply their matrix forms together first and then apply them. So that makes the job easier for you, or you can go through this entire recursive process. Another important detail I wanted to mention was that if a matrix is of dimensions m by n, that is, there are m rows and n columns, then the matrix takes, not for one, but the matrix takes your vector from Cn to Cn. Again, the use of C is sort of specific to our case. In most elementary linear algebra classes, they would instead say it takes it from Rn to Rm. Okay, so today we're going to start with inner products. An inner product is a process that takes two vectors, say V and W, and it returns a complex number, say C. It's complex because in quantum mechanics we generally use a complex vector space, but inner products are more general than the complex vector space, and there are real inner products as well. If you've done some basic physics, you will know of the dot product, which is in fact the inner product in the real vector space. But there are two ways to write the inner product. One is the more general function representation, and this is what people in most other domains will use. So in fact, if I was to remove sort of the angle brackets, if I was to remove those, this would be normal notation in another field. But this would also apply for quantum mechanics in terms of Dirac notation. So the inner product takes two complex vectors and returns a complex number. Within Dirac notation, we write the inner product also this way. And it does have a significance sort of that we have flipped one of them, that one of the kets has become a bra. It sort of represents a row being multiplied by a column. And I would think about that to get some intuition. Okay. So there are three fundamental properties of an inner product. One is that it is linear in the second argument. This is sort of an abstruse way, but I will sort of get into it, and then maybe it'll be a little bit easier to understand. So let's suppose we have some vector v, and then we take another vector, which is actually a linear combination of different values of this, or rather of different vectors in a particular set W. So this is actually a linear combination of vectors in W. And we're taking their inner product. This is actually just equal to summation over I of lambda I. Oh. Okay, I've run out of space over there, but okay. So that is the first rule for an inner product. The second rule, the way we're specifying this is sort of, it's very particular to a complex vector space, which is sort of just our circumstances currently. But there's a more general way to look at this. But particularly for a complex vector space, um, if you take the inner product of v and w, it is equal to the inner product of w and v, but take the complex conjugate of that. As I mentioned, this property will sort of vary across different vector spaces. For the real vector space, actually, this will work. Usually, we would just write in the real vector space. I won't write it because it'll be a little bit confusing, but in the real vector space, generally, we would say that the inner product between x and y is equal to the inner product between y and x. But you could just view that as the fact that the complex conjugate does nothing to real numbers. This is mostly because the set of real numbers is within the set of complex numbers. Okay. And finally, we can come to property concerning their norm. We've not gone to that too much yet, but so the inner product of a vector with itself must always be greater than 0, and it's only greater than 0 when v is equal to 0. That is the 0 vector. We actually use the inner product to represent the quote-unquote length of a vector. And so this sort of makes sense in that context, in that the length of a vector is never going to be 0, except if the vector is the 0 vector itself. So the inner product is defined very specifically on Cn, which is the general complex vector space. And Cn is what is known as an inner product space. Okay, yeah. So this is an inner product space. This means that it has a defined inner product. And so you may hear the name of a Hilbert space, but for our purposes, this is really just a finite dimension. We will only deal with finite dimensional Hilbert spaces, and these only have, and the important properties of these is that they have an inner product defined. So in particular, the inner product in Cn is, so if you take the vector y, and I'm actually taking this directly from Nielsen and Zhuang. It was a little bit easier to include their formulation. Rather than doing the vector manner, this is a little bit easier of an interpretation to look through, but I'll draw the vectors as well. And so the idea is that the first element of this vector is multiplied with the first element of this vector, and so on. It's kind of a slightly exhaustive proof to prove that the complex, the inner product as defined on the complex vector space satisfies the properties of an inner product. But I will leave that for you to try on your own. It's definitely an instructive exercise. Okay, so now we're going to actually take a quick diversion into projections in Rn, just so I can give you some intuition for the inner product and what it does. So in this video, we will mainly be using the dot product actually, which is actually a form of the inner product in Rn in a set of n vectors of real numbers. And we will also be using a concept called projections. It's probably not standard content at this point, but I feel like it will help get better intuition. Don't think too much about it, and I would probably even forget it after we talk about this, because we will have some different ideas of projections when we come to the more quantum mechanical part later. So I definitely don't want you to confuse those. So the inner product, what it does in general, is to tend to provide a sense of how similar in terms of direction two vectors are. And there's a good way to quantify this. So the dot product, if you're familiar, is written you just draw a dot where you would normally draw an asterisk, etc. for multiplication, and where a and b are two vectors of real numbers. I use this funny hat notation to indicate that they are vectors. This is the standard notation outside quantum mechanics. So if I take a dot b, what this actually gives us is, again, this transforms to a set of two vectors to a scalar or constant. But since this is an Rn, it doesn't produce a complex number, it produces a real number. So what it produces is, and over here, this term represents the length of A, and this represents the length of B. This theta is the angle between A and B, and this is the cosine of it. So if we sort of take this, as an on axiomatic value, you don't need to if you were to take a sort of a linear algebra class, but that would be too much detail to go into over here. So if we have two vectors, let's call it V actually. So V and A, then I can drop a perpendicular from V to A, and I can in fact make that another vector and call it V perp. It's not actually important that it's a vector, but whatever. And so of this length, rather this vector over here, from the start of A to the point on A at which V's perpendicular lands, is called the projection of V onto A. So it's the projection of V onto A. And so the question then would arise probably, how do you find this? This is the angle between V and A, theta. And if you look at it now, this is actually a right triangle. So if we simply take the length of V for a moment, V cosine of theta would be this length. Right? But this is a scalar. This is not exactly what we wanted. So instead, we would have to do V, the norm of V cosine theta times this vector A. And I'll write it this way. I won't use Dirac notation. Times this vector A. This is just so that we get in the direction of the vector A. However, we would then have to normalize this in the sense that we have to normalize the vector A. I used the term before introducing it, but to normalize basically means to get the length of a vector to 1. We'll discuss it more when we actually get into norm and orthogonality. But the important thing over here is simply that we are dividing this by the length of A, right? So that this does the introduction of the A vector over here doesn't actually impact the length of the vector that we wanted to draw. The thing is actually that we can represent v cosine theta times A more efficiently like this. And so the norm of A times the norm of V times cosine theta, you may recognize this form as actually being the dot product of those two. So we could just reduce it to that. A dot V times the vector A. Divided by the norm of A squared. So this is sort of an interesting formula. If for a second we can sort of abstract and forget that this is a dot product and instead take it as representative of an inner product, we can see that actually as A and V are more aligned, the closer they are, that is, the smaller this angle theta, the closer this comes to sort of reaching the entire length of V. That is the longest possible vector being the projection, the longest possible projection, that is, when V and A are in the exact same direction. And so what you realize is when these vectors are closer together, they have a smaller dot product, or rather they have a greater dot product, and this dot product is usually positive if the angle is acute. And this also has to do with this cosine theta over here. Okay, so now we're going to discuss orthogonality. And as you may have already guessed from the section on projections, um, the inner product of two perpendicular vectors, as given here, is going to be 0. And the reason for this is because they are in no way in each other's direction. There is no sort of, first of all, it becomes sort of difficult to draw a perpendicular line in the first place, because that coincides with the original line. And effectively, they're in no way in the other's direction such that they don't coincide at all. And so therefore, there is 0 as their inner product. So we will use this to see whether a particular set of two states, for example, are orthogonal or not. I also wanted to bring up a couple of other important definitions that have been mentioned but not elaborated. This represents the norm of vector V. In terms of a vector space, this looks like actually just the length of this vector, so this distance. But the norm is actually in the complex vector space, and in general actually is represented as the square root of the inner product of the vector with itself. And maybe this makes some amount of sense. It's like, how much is the vector in the same direction as itself? Well, it's somewhat related to its length, and in this case, it happens to be the square of its length. So we take its square root in order to get the norm. And I also mentioned this process of normalization last time. And basically, the idea is that now that we know what the norm is, the normalized version of any vector is the vector divided by its norm or magnitude. this basically reduces it to what's called a unit vector, meaning that the magnitude of this new vector, let's say it becomes W, and I'm using the standard vector notation, but you could switch this over to Dirac notation. And then the magnitude of W is going to be 1. And we will also use this idea of a set of orthonormal vectors. So a set of orthonormal vectors is basically a set of vectors in which every vector is mutually orthogonal with every other vector. That is, for any v1 v2 in this set, v1, the inner product of v1 with v2 is going to be 0. So this makes them mutually orthogonal, and they're an orthonormal set, meaning that for any v1 in the set, the magnitude of v1 must be 1. Basically, all of them are unit vectors. There's a last quick footnote, and this has been sort of a section of footnotes, but these are sort of important. And there's this particular symbol that we will on occasion use. It's called the Kronecker delta. And basically what the Kronecker delta does is it takes two usually iterable values. That's where we find most use for it, but in general, two values. And it tells you if these two, it takes their inner product effectively. And if these two are in the same direction, it returns 1. If these two are orthogonal, it returns 0. So when we have a set of orthonormal vectors, we can sort of apply del ij to check whether we have reached a particular, whether I is equal to j, because that's the only case when we're going to have 1. Otherwise, we're always going to have 0. You can maybe think about why that is if it doesn't. So we've been discussing linear algebra thus far, and for the first time, we're going to introduce what would be really a linear algebra algorithm. And we're going to type this, actually. It'd be a little bit easier for you to read. But we're going to be exploring the Gram-Schmidt procedure. And this is a really key idea in linear algebra in general, and especially as abstract linear algebra. So let's get into it. In particular, let's talk about a particular vector space V, where we have a set of basis vectors. Let's say Wi is a representative element of that set, but it would be like W1 to Wn, right? And what we want to do with our Gram-Schmidt procedure is we just define what a set of orthonormal vectors are. That is, every vector in this set, so for example v1 or w1, is going to be perpendicular to every other vector in the set. So w1 is going to be perpendicular to wn, it's going to be perpendicular to w2, and so on. And every one of these vectors is also going to be normal, meaning that its magnitude is 1. Okay, so this is the idea. But right now, what we have, what the Gram-Schmidt procedure assumes, is that you have a set of basis vectors, but not necessarily one that is entirely orthonormal. The point of the Gram-Schmidt procedure is to take a set of basis vectors and to produce an orthonormal set of basis vectors from them. So here's what the process is. So we call our first vector of the new basis, which is going to be orthonormal, v1. Let me just write that a little bit below so I have some space. v1. And we set this equal to w1 divided by its magnitude. Right? Nothing too special here. All we're making sure is that, our first basis vector is normalized. That's really all we're doing. We'll deal with orthogonality with all the vectors from here. And from from k, for some I k, where k goes between k is greater than 1 and is less than equal to n, where n is the number of basis vectors, that is the dimension of this vector space, we say that v of k, rather, actually, we would write this as, let me fix that. We would write this as v sub k plus 1. So let me just write this out, then I'll write the range. Okay, v k plus 1 is going to be equal to w at k plus 1 minus, so the summation over I, that's an I, of the inner product between vi and w. Okay, this is kind of getting crammed. Let me rewrite that really quickly. So v k plus 1 is equal to w k plus 1 minus the summation over I of the inner product between v sub I and w k plus 1 and multiply this by v. And then we would normalize this. But before we get to that, this I actually goes from 1. So it starts with that first vector we defined before, where we just normalized it, this one, this vector. And then it goes till the vector that is right before this. That is, I goes from 1 to k, basically. And what we're doing is, for every vector in our new basis, we are taking, essentially what we are doing is we are taking the part of w k plus 1 that is in the same direction as v sub I, and we're removing it from w k plus 1. So by doing this, at the end of the process, what we have done is we've received a new vector that is orthogonal to all the vectors that came before it. And if this doesn't make sense, think a little bit deeper about the way we come up with a description for a vector even within a normal basis. For example, the inner product between I and v, where I is the standard basis vector in the x, usually representing the x-axis in a 3D vector space. Then v, then basically if we had a, really I could be any basis vector, but if v was a list of numbers, if we come back to that, components, then the one of these components that actually corresponds to multiplying this basis vector I, its component value would be, component value as in this component value, would be obtained by taking the inner product of I with v. So that's essentially what we're doing here as well. And since we want every one of these to be normal, we would just take this entire top expression and just put it down here and take its magnitude and divide by it. So that way we have a completely normal, a set of orthonormal vectors. So we just concluded a series of discussions on the inner product. But another key topic in linear algebra is what is called the outer product. Now, we will definitely not go into as much detail with this as we did with an inner product. It's maybe not as essential, but we will use it a lot to, we will sort of write matrices in outer product form. So it's definitely something you'd want to know. So let's consider the case where we have a vector v rather, let's consider the case where we have a vector w first, and I keep writing in the order I didn't want to write them. Okay, so v and w, and then let's take the ket w. Basically, this is an inner product, so this should return a constant, which then multiplies this vector, right? But we could rewrite this, since it's a constant, the order, since one's a constant and one's a variable, the order doesn't really matter. So we can rewrite this way, correct? And if you think about the way an operator appears, generally we write an operator as in this way, right? Some operator A applied to the ket W. So let's look at the form of this, and this in fact actually can be perceived as just an operator. So you can take this and apply it to W. And this actually is the outer product operator. And so now this is sort of, definitely kind of confusing, and it doesn't make a whole lot of sense initially. I had the same experience, but you can sort of you'll sort of start to find more use for it once you start using it in compressing or expressing matrices or linear operators. Yeah, the only other thing I wanted to mention about outer products for now was that the linear combinations of outer product operators also actually produce other operators. So if we were to take, some I, we could produce another outer product operator. This would be another outer product operator. Okay. Next, let's cover. Okay, so now we're going to talk about famous Pauli matrices or Pauli gates. So these are really important in quantum computing, especially since they represent actually the fundamental operations that is, relating to the NOT gate and particular types of rotations. So we can quickly cover those matrices now. I definitely don't always remember them. I am referring to the Wikipedia page right now. It becomes kind of difficult to remember them sometimes. But as you use them, you'll know what the more commonly used ones are. So this is the first Pauli gate or Pauli matrix, and generally we write the Pauli matrices as 2x2 matrices. And you will probably recognize this if you've taken any other kind of matrix class. And I also did briefly describe it. This is the identity operator, and it's in fact the identity matrix here. This is the Pauli. It's often called the Pauli zero matrix. So for all Pauli matrices, we use this symbol called sigma. And so Pauli subscript 0 is Pauli subscript 0 is the identity matrix. Okay, then we come to the X matrix, which after the identity matrix is one of the most used, where we have 0, 1, 1, 0. And when we were doing we were trying to understand how you can derive a matrix form of a linear operator using its effects on the initial basis. I actually did derive this matrix. Let me just remove all these lines. But basically, in quantum computing, this matrix represents the X gate, or basically the analog of the classical NOT gate. And when applied to any of the basis vectors, it flips them of C2. It flips them to the other one. So we call this the X gate or matrix. I'm calling them all gates because actually they're represented as gates in a circuit, So we would write this as like x, for example. And then you would have one qubit going in this way, and you'd have another qubit. You'd have the same qubit, flipped coming out over here. Okay, so this is the poly X matrix. Then we come to the what I like to call the slightly more esoteric ones. There is the poly Y matrix, which is zero minus I, and zero. So this is called the Y matrix. I won't give too much explanation on the last two. It's kind of difficult to see what they do for now. In the future, when we discuss different computational bases, you'll start to see why they can be just as useful as the X, or definitely more useful than the identity gate. The final one is the Z gate, which is 1, 0. There you go. 1, 0, 0, minus 1. So this is the Z gate, or the poly Z gate. And those are the four poly matrices. Let me just give you a quick overview. Yeah. So you will use these a lot, especially in, these are like the favorite matrices for any kinds of derivations or anything like that. So you'll probably end up using them to. Okay. So this actually comes after a failed attempt to record that part. So I will quickly sort of go through what I have written here. And I'll make it a little bit easier to understand. So effectively, eigenvalues and eigenvectors are a very important concept in quantum mechanics, and especially in quantum computing. In particular, they're involved in sort of the way we measure qubits. That is the way we condense their superposition, or collapse their superposition would be the proper word. But let's just get into the nitty-gritties of them before we get to all of that. So let's take an operator A and apply it to this vector V. And the important thing about this vector V is that it's specially related to A, in that when you apply A to V, what it does is, we have this vector here, and let's assume this represents V. What A does is it simply scales it. So when you apply A to V, you get a vector in the exact same direction, just with a different magnitude. And so these vectors are interesting, and they're called eigenvectors. So this is exactly the kind of vector we're assuming we have over here. And so this is simply a statement of the same thing. We're scaling this same vector by some particular value lambda. And this value is called the corresponding eigenvalue of this eigenvector. Okay, so how do we find an eigenvalue? First, we take A applied to V, and usually we will think about this as a matrix from here on, mostly because we're going to actually do some sort of more practical work, and thinking of it as a linear operator is a little bit cumbersome then. So A applied to V minus lambda times V is then equal to 0. It's simple algebra here. And then we can say, we can combine these into a single matrix, in that A minus lambda I, where I is just the identity matrix, applied to V is equal to 0. And just for a second, let me call whatever is inside this, parentheses, let me call that B. I have these strange blind spots on my computer, that's why it's looking so weird. But so let's call it B, and let's apply B to this vector V over here. And it's going to produce 0, right? This is what our previous equation says. If there was an inverse to B, now I'm not entirely sure how comfortable you are with the idea of an inverse, but basically with respect to matrices, an inverse of a matrix basically performs the opposite operation as it. So if we take B inverse and then we apply B, it's just going to have the effect of I. That is, it doesn't do anything. right? I just leaves the state as it is, and that is exactly what a matrix multiplied by its inverse is going to do. So if such an inverse were to exist, then we could say that B inverse times B times V is equal to B inverse applied to 0, right? We're applying it on both sides. And so B inverse B would become I. And so we'd just be left with V on the left side. And on the right side, we'd still be left with 0 because 0 is effectively an eigenvector for all linear transformations. And so what we're left with is that V is equal to 0. And this is really a trivial result. We really don't care about this and we don't want that. Which is why there's this humongous crossover there. We're going to try to avoid that. So the way we sort of avoid that is this condition called the characteristic equation, in which we decide that the determinant of this matrix, what I call B over here, A minus lambda I, has got to be 0. Now, I'm not going to get into exactly why we do this, but maybe for some intuition, you could think about this. So the determinant for a 2D matrix is essentially this. And I'll show you what that means in a second. We'll do an example. And so when we multiply this by rather when we divide and so we sort of perform some operations to a main matrix. This is all to produce its inverse. So basically what we're doing by setting the determinant, which is at the bottom over here, by setting that equal to 0, we're basically saying that this inverse is impossible. And so that we can stop getting that 0 as our answer. So this is our characteristic equation. So let's just try and apply this, and then maybe you'll get a better intuition. So let's take the Z, poly Z gate or matrix from before, which is 1, 0, 0, minus 1. So first of all, we go through the entire, the motions. Z applied to V is equal to lambda V. Z minus lambda I applied to V is equal to 0. And so the determinant of Z minus lambda I is then equal to 0. We're setting it equal to 0, rather. Okay. And so just to repeat this formula, the determinant of a 2D matrix is AD minus BC. And where this comes from is if you have a 2D matrix, you can sort of just write these mnemonic characters here and sort of remember what a determinant is. And so that's a D. I can't close it. That place doesn't allow me to write. But basically, we just need to take this particular algebraic expression, and that produces our determinant. So we're just going to do the same thing for this Z matrix. So we're going to take 1 minus lambda, which is in the position of A, and multiply it with negative 1 minus lambda, which is in the position of D. And both B and C are 0, so we can just ignore that term. So then we get negative 1 plus lambda minus lambda, which is 0, plus lambda squared. And so here's where I made the mistake. And everything spiraled out of control here. But I basically was supposed to have written that lambda squared minus 1 is equal to 0. And so we can stop dealing with imaginary numbers for eigenvalues and throw out all of this stuff. So what we do instead is that lambda is equal to plus or minus 1. So let me try to write here instead. So if lambda is plus or minus 1, so now let's take the case where lambda is equal to plus 1, right? And so now we just go back to the application of the matrix. We have the matrix 0, 1, 0, 0, negative 1. And let's apply it to some representative vector from C2, AB. So when we apply this, we produce another vector, which is A times 1 plus B times 0 for the first component, which is going to be A. And then A times 0 minus B, which is going to be negative B. Okay, so now that we have this, we are going to equate this to lambda times AB which is really just going to be 1 times AB. So I can just remove that, which then means that, ignore that, which then means that A is equal to A. Doesn't tell us too much, but negative B is equal to B. And so that's an automatic giveaway that B is equal to 0. The thing with sort of the way we would find A at this point is that we want a normal vector out of this, right? We could get any scalar multiple of it, and it's going to be an eigenvector anyway. So if we take, we have B equals 0, and so, we have A squared plus B squared, which must be equal to 1, right? This is our normal condition. That is that the magnitude of each of, sort of the inner product of this with itself must equal 1. And so if we actually just do that, it would be A, B. This is kind of funny notation for this. You wouldn't normally write it this way. But I'm just writing it so that we can maintain the inner product syntax that we were using. But basically, you would apply A with A again and get A squared and add it to B times B, which would be B squared. So this, we want this inner product to be 1, right? Because we want it to be normalized. And since we know B is equal to 0, A is really equal to positive 1. It could be negative, but that's not really a very useful case. It's not much different. So on the other hand, lambda could be, so that's our first eigenvector eigenvalue pair. The eigenvector is, let me just quickly write that out, 1, 0. And this is the neatest set of bases. This is the neatest basis set for C2, which is why I keep using it everywhere, and which is why it keeps popping up all over this this primer. It is actually the most standard basis, and we definitely use this a lot in quantum computing. On the other hand, we had the other eigenvalue, which was that lambda is equal to -1, right? And so we can just go through this entire process as it was again. So 1, 0, 0, -1 applied to AB. And so that gave us A and minus B, right? And we were then equating this A minus B with AB before, but now that we're multiplying by lambda equals -1, where we get negative A and negative B. So let me just move this over a little bit. And so what this essentially means is that A is equal to negative A, and, yeah, A is equal to negative A, and negative B is equal to negative B. So we can cancel this out, and it shows us that B is equal to B. That doesn't tell us too much. On the other hand, this indicates that A is equal to 0. So we can go through the same process as we did with the previous eigenvector. And that should tell us that our new eigenvector is 0, okay, 0, there we go, 0, 1. Right, so these are actually this is the computational basis, which means that it's the standard basis we usually use. And as I mentioned before, this, which is often referred to as 0, actually represents the 0 state of a qubit. And this represents 1, which is the 1 state of a qubit. And so when we're measuring, we will often collapse a qubit superposition, which is actually a linear combination of these two. So you can see that a lot of this will apply quite directly into either one of them. And yeah, we've covered eigenvalues and eigenvectors reasonably thoroughly. Just another final remark. There's this concept of an eigenspace. So for every eigenvalue of a particular linear transformation, there is what is called an eigenspace. This is the set of all vectors within the domain of a linear operator, which are basically eigenvectors and have this eigenvalue, right? that are eigenvectors to this linear operator and have this eigenvalue. You could have what is called a degenerate eigenspace, where you have more than two or more um, linearly independent eigenvectors as the basis for this eigenspace, but